Hello, welcome to this video. In this video, we will learn about ideal gas mixture. An ideal gas mixture is a mixture of two or more gases where each gas behaves as an ideal gas. So, a good example of an ideal gas mixture is air. In air, we have nitrogen, oxygen, carbon dioxide and many other gases in small percentages. So, do we call it as an ideal gas mixture? Yes. If each gas behaves as an ideal gas and if they do not chemically react with others and the gases mix perfectly, but each gas behaves independently, in that case, we can call the gas mixture as an ideal gas mixture. Alright. So, the assumptions which we make while calling a particular gas as an ideal gas mixture is each gas in the mixture should follow ideal gas law and there are no intermolecular forces between different gases and total properties of the mixture is sum of properties of individual gases. In that case, we can call that mixture as an ideal gas mixture. Alright. So, we have tried to show the same here. There could be gases which is a mixture of many gases. Alright. Let us talk about Dalton's law of partial pressure. According to Dalton's law of partial pressure, what do we mean by partial pressure? Let us talk about that. According to Dalton's law, partial pressure is defined as the pressure of gas component. Let us say a mixture we have and mixture has got three components, namely one which is indicated by red, blue and green. So, there are three gases which are mixed in this gas mixture. So, when do we call a partial pressure? So, if a gas component would exert pressure like the same volume is occupied by, let us say, if this total volume is occupied by only one gas, let us say gas A, okay, then what would be the pressure it exerts on this volume is called as partial pressure. Alright. According to Dalton's law, partial pressure is defined as pressure a gas component would exert if it alone occupied the entire volume of the mixture container at same temperature, remember, at same temperature. So, here temperature is same and volume of the container is same. If the total volume is occupied by only these red molecules, then what would the pressure would be? So, that is called as partial pressure of gas A. So, similarly, what would be this blue molecules? So, if it occupies the whole volume on itself, by what is the pressure it exerts? So, then it is called as partial pressure of this particular gas. So, total pressure will be equal to sum of this partial pressure. So, P1 indicates the partial pressure of this gas plus P2 plus P3 here. Okay. Very important, at same volume. So, volume of the container should be same and temperature is same. So, partial pressure of each constituent is defined by pressure of gas component would exert if it alone occupied the entire volume. Alright. So, the total pressure will be sum of all partial pressures. Now, let us move on. Amagat's law of partial volume. Now, total volume, see, if this is once again we have considered a mixture of gases in this container. Now, total volume will be sum of volume of each gas would occupy individually at mixture pressure and temperature. So, at same pressure and temperature, we will have volume of each molecule, right. So, total volume will be volume of each constituent V1. So, let us say this is 1 V2 plus V3. Now, very important, at same pressure and temperature, we are not changing pressure and temperature. At same pressure and temperature, if particle 1 occupies what is its volume, if you can measure that, that will be V1. At same pressure and temperature, if you measure the volume of blue molecules, then that will be V2 and so on. So, total volume will be V1, V2 and V3, and most importantly pressure and temperature are same. This is very much needed in order to derive gas constant for mixtures. So, please understand that this concept is important for deriving our mixture. So, at a given temperature and pressure, the total volume occupied by the mixture of gases is equal to sum of individual volume that each gas would occupy on its own. So, V total will be equal to V1 plus V2 plus V3. This is called as Amigat's law of partial volume. Now, let us talk about few of the definitions which are in ideal gas mixture. Mole fraction. So, if we consider a gas mixture which has got constituent like A, B and C, and then let us say number of moles of A is like 50, number of moles of B is like 30 and this is 20. We are deliberately keeping it to make it like 100, but in reality it could be different. But what we mean here is, it is the ratio of number of moles of that particular gas to the total number of moles. So, mole fraction of A, mole fraction is denoted by mu. So, mole fraction of A is number of moles of A divided by total number of moles. So, here it is 50 divided by 50 plus 30 plus 20 is the total number of moles, that is 100. So, you will have 0.5. Similarly, mu B is the mole fraction of B. So, that will be 30 by 100 which is 0.3. Similarly, mu C, number of moles of C divided by total number, that is 20 by 100, that is 0.2. Now, remember, it is telling us the ratio of the mole number of moles to the total number of moles. It is something like 50% of the total moles is A, 30% of the total moles is B and 20% is C. So, obviously, if we add mu A, that is mole fraction of A plus mole fraction of B plus mole fraction of C, it will be equal to 1. Because it is after all, what is the percentage of these gases in the total mixture. Similarly, mass fraction, if we consider a mixture of A, B and C, let us say the ideal gas mixture has got constraint like A, B and C, then mass fraction of A will be equal to mass of A divided by total mass. Now, similar examples I can take. Let us say this is 30, this is 20 and 50. So, mass is here 30 to the total mass of 100. So, mass fraction of A is 0.3. Similarly, mass fraction of B is mass of B divided by total mass, that is 20 by 100, 0.2. Similarly, mass fraction of C is equal to mass of C divided by total mass, which will be 50 by 100, 0.5. So, similarly here, if we add mass fraction of A, B and C, it has to be equal to 1. Now, let us move on to volume fraction. So, we can write this if you want mass fraction of A plus mass fraction of B plus mass fraction of C is equal to 1. So, volume fraction, it is again the same concept. Volume fraction is again the ratio of volume occupied by that gas to the total volume. So, volume fraction of A, if you want volume of A divided by total volume. Similarly, volume fraction of B is equal to volume of B divided by total volume. Volume fraction of C is equal to volume of C divided by total volume. And remember again, volume fraction of A plus B plus C must be equal to 1. Now, let us move on. We have few more definitions. Equivalent molecular weight. So, we are talking about a mixture. So, molecular weight of a particular gas may be known to us. For example, in a ideal gas like mixture like air, we have oxygen, nitrogen and let us say carbon dioxide. Now, oxygen we know, alright, oxygen is 32, nitrogen is 28 and carbon dioxide is 44. Now, what would be the mixture molecular weight? That is what we are interested in. The equivalent molecular weight is defined as total mass of mixture. So, total mass of mixture, equivalent molecular weight of mixture is the ratio of total mass of mixture divided by divided by number of kilomoles that is present in the mixture. So, that is N. Okay. So, or we can also use molecular weight of mixture is sum of all mole fraction multiplied by molecular weight of that particular gas, which is something like if you have 3 gases, then it will be like mu1 molecular weight of first gas plus mu2 mole fraction multiplied by molecular weight of second gas and so on. Okay. Now, similarly, let us go for ideal gas equation for mixture. An ideal gas mixture also follows ideal gas law. So, it is PV is equal to M R T, where this is R of mixture. Obviously, pressure is total pressure, temperature is not going to change for each ideal gas, and we are talking about volume of mixture here and mass of mixture. All right. Now, gas constant of a mixture, that is R. So, gas constant is defined by the ratio of universal gas constant R bar by molecular weight of mixture. So, it is the ratio of universal gas constant to equal molecular weight of the mixture. Okay. Now, partial pressure formula is also like this. Let us say we have gas like ABC, mixture like A, B and C. Then partial pressure of A will be mole fraction of A multiplied by total pressure. Partial pressure of B will be similarly mole fraction of B multiplied by total pressure. All right. We will move on to a derivation. Derive an expression for gas constant R of a mixture of a gas. So, we are interested in deriving R mixture. Okay. So, we already know Avogadro's law. So, from here we will start deriving. According to Avogadro's law, we know that the volume of ideal gas mixture is sum of all constituent gases, and very importantly at same pressure and temperature. Okay. Now, keeping that in our mind, let us write an equation for an ideal gas. PV is equal to M R T, and this is R mixture. For ideal gas mixture we have written. For ideal gas mixture. Call this as equation 1. Now, similarly, if there is a mixture, as we said, let us say it has got constituent like A, B and C. For first particular gas, we can write pressure, volume of A is equal to mass of A, then R of A and temperature. Remember, pressure and temperature for a mixture is going to be same if we are talking about Avogadro's law. So, let us call this as equation 1. So, can we write the same equation for constituent B? So, P VB is equal to MB, RB and T. Very important is this factor. We are not giving suffix A or B to pressure and temperature, because in all of this pressure and temperature is going to be same. So, similarly for C, P, VC, MC, RC and T. Now, let us call this as equation 4. Now, what we shall do, divide equation 2 by equation 1. Now, what we will have, PVA is equation 2 and MA RAT, and if we divide this by equation 1, P total volume here and total mass here, R mixture and temperature. So, that is what we did. Let us cancel out this pressure, total pressure, this temperature, then we will remain with VA by V here is equal to MA by M. I am calling it as mass fraction of A, and let this be RA by R mix. Okay. Now, let us call this as equation 5. Similarly, let us say divide equation 3 by equation 1. So, what we can have is PVB is equal to MB RB T, and here is PV is equal to M Rmix and temperature. Okay. Now, pressure cancels out, temperature cancels out. This VB by V, I will keep it as it is. This is MF B, mass fraction of B, and let this RB by Rmix be there as it is. Now, let us call this as equation 6. Let us call this as equation 6. Now, let us similarly divide equation 4. Divide equation 4 by equation 1. Then what we'll have is PV suffix C divided by PV is equal to MC RC T divided by total mass R for mixture and temperature. So, pressure cancels out, temperature cancels out. Vc by V, I will keep it as it is. This is mass fraction of C. Then we have RC by R mixture. Okay. Now, let us call this as equation 7. Now, if you look at 5, 6, 7, we can add 5 and 6 and 7. So, 5, 6, 7 will add. So, on left side we have VA by V plus VB by V plus VC by V must be equal to mass fraction of A. We can take this common, by the way, R mixture we can take common in all the terms. So, 1 by R mix we can take common, and remaining thing I will write it here, mass fraction of A, R of A, plus mass fraction of B, RB, plus mass fraction of C, RC. And remember, these are volume fractions on the LHS. VA by V is VFA. So, this summation is like in the numerator also VA plus VB plus VC will be equal to V. So, this turns out to be 1 this side. Alright. So, R mixture comes to the left if you want. Then you will have MFA RA plus MFB RB plus MFC RC. So, that is the expression we wanted. So, we wanted an R gas constant for a mixture is given by mass fraction of each gas multiplied by R of that particular gas. If you sum it up, you will get the equation for R for a mixture. All right. Thank you.